This video is going to look at differentials, and I gave you a preview of differentials in the previous video with the tangent line approximation. And here I want to go into a little bit more detail about what our differentials are. And you'll notice here once again we're using the same equation here of our tangent line at some point C f of c. And we have our, basically this is your point slope, y minus f of c equals f prime of c times x minus c. This equation, just like we did before, is used to approximate the graph of our function f, and the quantity x minus c is the change in x, which we denote by delta x. And when delta x is very small, the change in y is denoted by delta y, which can be approximated by dy. So if you look at the formula below, delta y is going to be f of x plus delta, f of c plus delta x minus f of c. So here we're evaluating c plus delta x and c. That's your x values. So we're going from one x to the other. So if we plug it into the function f, we're taking essentially here subtracting our two y values. And we're going to look at today how we can approximate this actual change in y, the delta y. We can approximate that with dy, which is our differential here. This is our differential dy. And this is going to be approximately equal to the derivative f prime of c multiplied by delta x. So to look at this a little bit more detail, let's look at the graph we have here. Here I give you the graph of f of x is equal to the square root of x. So here is y equals the square root of x. And I've already drawn in the tangent line here. That's our approximation. And we're looking at this point C. And to define some terms here, if we go from C to C plus delta x to another point on the graph, this would be our delta x. This is the actual change in x. So we're going from one blue dot to this other blue dot. This is C to C plus delta x, so that's giving us delta x. And then if we go from here to here, notice here we're going from f of c on the y-axis up to f of c plus delta x. And that's where we get f of c plus delta x minus f of c. Up here in the formula, f of c plus delta x minus f of c. So that's simply delta y. That's the change in our y. F of c plus delta x minus f of c. So all of this is based off of the actual function y equals the square root of x. Now, before I go any further, one thing I do want to point out is that when you look at this graph, I want you to keep in mind, because you're thinking, well, wait a second, delta x, that looks pretty large from c to c plus delta x. But I want you to realize when I pick these points, if this is point C on the graph, then when I go over a distance of delta x, you can really think of this as picking another point that is here. At this point, this would be our c plus delta x. Realize we're thinking about picking values that are extremely close. Now on the graph over here on the right, I've had to separate this so you can visually see it, but realize that the c plus delta x is really a point that's really much closer to c, okay? We're looking at a very small change in our x value. So here I've just blown this up so we can actually visualize and see the points. Okay, so keep that in mind. I know that's going to always be a little confusing because you're thinking, well, that's a big change in x. But this is really a small change in our x value. Now, these are the actual changes in the functions. We want to actually relate this to the approximation here, the tangent line in red. Well, if you notice, if we go from C at this blue dot and then we go to c plus delta x based on the green dot on the approximation. Well, the distance here from this blue dot to the green dot here, as far as your change in x, that's going to be the same. So this distance here, delta x, is going to be equal to, and we'll call this dx, that's our differential of x, so that's the change in the x. And then if we go up to the green dot, then that means we're going here. What is the change in our y? Then this is going to be our differential dy. So if you notice, delta y is different from our differential dy. But we're going to show you where this is actually a pretty good approximation. Now, keep in mind, you're thinking, well, this is a big change here, but remember, this point is really very close down here. So if you notice, there's not much of a difference between those 2 points if we think of this green point being all the way down here somewhere. So what does that mean based on our formula up here for this differential dy? What this is really telling us is we're approximating again using our differential dy. We can use that to approximate the change in our y value. Now you'll notice the change in our x, delta x, and we call this the differential dx, is going to be equal because we're going from the same x value to the same x plus delta x value. So let's look at this in terms of our function f of x equals the square root of x. If we think of this as y equals the square root of x, then we can simply take the derivative of y, which would be dy dx, and this would be the same as x to the 1/2, so that would be 1/2 x to the negative 1/2. And that's how we've been taking the derivative. This is we're taking the derivative of y with respect to x. Well, now we want to find what we're calling this differential dy, the actual change in y. That's simply going to be equal to 1/2 x to the negative 1/2, and then all we're going to do is multiply by the change, this differential dx, the change in x. So then we would just multiply the dx on the right. And this here is your differential dy. And this is approximating the change in your y. And that's what we're indicating over here. This is your dy. This is the change in our y value. And that's why up here in our formula, dy is approximately f prime of c delta x. And remember, this is dy's. We could think of this as being approximately f prime of c delta x. Remember, we're saying delta x when we're talking about very small values. That would be the same thing as dx. Okay, so that's all that we're talking about here with your differential. And if you need to, go back and look at and study this diagram of the graphs on the right, where we have the graph of our function and our tangent line, and realize we're simply using this tangent line as a way to approximate values here on our function, the square root of x. And once again, I want to stress it another time, is that we need to keep in mind that this delta x is an extremely small value. And all we're doing is looking at the change in our x, and then we can use that to calculate our differential dy by taking the derivative of our function and multiplying it by dx. So you may want to go back after watching this video, you may want to go back and look at the example of our tangent line approximation in the previous video.